All right, let's get started. Today it's our pleasure to have Leane. She's a postdoc at MIT working with places last year. She started her physics career as a student at the University of Melbourne, working on dark matter searches at the LHC, but later she shifted to astrophysical searches, and she's going to tell us about a very persistent topic, which is the gamma signal from Galactic Center.
Great, thanks. Hi everyone, thanks for the invitation to speak today. It's a pleasure to be here. So today I'm really excited to tell you about some research I've been doing to understand exactly what might be happening in the center of our galaxy in terms of these mysterious excess GeV gamma rays. So the bulk of what I'll tell you about today will be based on this paper here, but I'm also going to give you a sneak peek into some of the work I've been doing since to try and get to the bottom of exactly what might be happening. So this features work I've done together with Tracy. Okay. So first of all, the Galactic Center GeV Excess is an excess in GeV gamma rays. It's highly statistically significant, so we definitely know it's there. It's detected by the Fermi Gamma Ray Space Telescope. So one of the great things about the Fermi data, as you might know, is the data is publicly available. So you don't have to be a member of the Fermi collaboration to access the data, to download it, to do any sort of analysis you might like to do. In fact, this is actually how this excess was first found. So back in 2009, two theorists, Dan Hooper and Lisa Goodenough, downloaded the data and expected just to set some mundane dark matter limits, as we kind of get used to doing a lot of these days. But instead they found something really interesting. Instead of just setting bounds on dark matter, they found an excess. And they didn't know for sure it was dark matter, but they knew something was there. And in the time since this was first discovered, which is now 10 years ago, there's been considerable debate in the literature as to what we're actually seeing. Are we seeing a dark matter signal, or are we seeing something else? So a few years after this was found in 2009, there was a compelling case for dark matter paper that was put out. It's the Damon and L paper. So you can see this is the excess here in the center of the galaxy once you remove the expected backgrounds. But the question that still stands today is, what is this excess? Is it dark matter, or is it something else? And within the community, while we might have a lot of debate, there are a few features that are generally at least approximately agreed upon. One thing is its morphology, the signal. So the signal is, depending on how you do your diffuse, so your background modeling, can be taken to be approximately spherically symmetric around the center of the galaxy. It scales like an inverse power law, so that's what you can see happening here. So this is you going out further in galactic latitude, so further away from the center of the galaxy. What does the signal look like? So it's dropping off inverse power law, and it extends out to at least around about 10 degrees from the center of the galaxy. And what's nice is this can fit a generalized NFW profile. So an NFW profile is just a really common density estimate for the dark matter profile, how the dark matter is distributed. Something else is the spectrum of the signal. So one thing you might also wonder is, well, we said we have some excess, how do we not know it's just coming from lots of different things? So a study was done in 2014 to just break the sky up into different regions. So that's what this plot is showing. So this is just latitude and longitude in the center of the galaxy. So just going out to 20 degrees, break it into different regions, and have a look. What does the energy spectrum, so the spread of the gamma rays, what does it actually look like? And what they found was it generally looked consistent, is that it looked like it was the same thing giving us this excess. So what you see on the plot here, this is just the energy, and this is the E squared DND, which is just like how much of the gamma rays you have, the number of particular amount of energy. And you see in different regions, generally it looked like it's the same sort of thing. We have this general sort of spectral shape that we expect as a signal. Also in terms of the intensity of the signal, it's very interesting from a dark matter perspective because you can actually describe this really well with just a vanilla particle dark matter candidate. So just your thermal particle dark matter. So this is the dark matter that was in thermal equilibrium in the early universe and froze out with some weak scale cross section. And you actually see, depending on what dark matter might be annihilating to, the cross section you expect for this WIMP, so particle dark matter, is actually about this size. And you can fit this really nicely with these different dark matter different annihilation channels. And that's what this figure here is showing. Depending on what dark matter mass you have, different final states can fit best, but we generally are converging on something that looks around, say, 50 GeV roughly, with roughly the thermal relative cross-section. So this is going to be bar. So anything that gives you a lot of photons gives you this general sort of spectral shape. So maybe you can see why so many people in the field are getting really excited about this, maybe actually being a signal of annihilating dark matter. First of all, it can be spatially consistent. It's roughly spherically symmetric. It extends well out the center of the galaxy, which is kind of what we expect from some dark matter candidate. Of course, we also expect that dark matter, if we have it, it should be built. There should be a lot of it in the center of the galaxy. So so we should expect to see a large signal if it's annihilating dark matter. We can fit the intensity really nicely with this thermal particle dark matter. And really, if this is dark matter, this would be the first evidence we have of its interaction with the standard model. So to date, we only have evidence from dark matter from its gravitational interactions. So it turns out, we could say today, we know this is a dark matter signal. The implications of this for particle physics, cosmology, everything about physics as we know it are really massive. So this is something we want to get to the bottom of. Is it a dark matter signal, or is it something else? So it could indeed be something else. And the leading alternative hypothesis is something called point sources, in particular millisecond pulsars. So millisecond pulsars, just really old neutron stars that are spun up with millisecond periods. So the reason we think, so when I say point sources, I'll be saying point sources instead of millisecond pulsars. Millisecond pulsars is what I mean for the rest of the talk when I say point sources. So the reason this is a favored alternative is, first of all, there were 2 studies in 2015 that found evidence for small-scale power in the center of the galaxy. So when I say small-scale power, I effectively mean clumpiness. So if you have point sources of these pulsars, you could expect them to be arranged in more of a clumpy signal because, for example, in one part of the sky you might have none of them, and another part you might have a lot. So the signal would look more clumpy if it were pulsars, compared to dark matter, which could just exist in a smooth halo. So I told you all about how dark matter fits these properties really nicely. Turns out pulsars can also actually do this, and I think this is the most compelling piece of evidence for point sources, particularly millisecond pulsars, is their gamma ray spectrum actually can match this sort of shape as well. And of course, we know pulsars exist, so you could start saying, well, their shape's the same, we know they exist, maybe that's just the answer. But the thing is, it's actually really not that simple, because there are a few sort of features of pulsars that don't match the signal. So, for example, such as how you get the right number of these pulsars to explain the size of the excess, but also how you get their distribution. So on their number, a particular argument usually that we discuss is why we don't see these low mass X-ray binaries. Now what I mean by that is we know about the millisecond pulsar sort of formation history just from looking other places in the universe. So whenever we see these, they're always in these, when they're being made, they're in this low mass X-ray binary state. So exactly what that means is you have, in its early stages, a millisecond pulsar is existing in a binary system with some other star, and that can then speed up. So it's a really old dead neutron star and it gets spun up until it becomes these millisecond periods. So whenever you look other places in the universe, you always see some of these things emitting an X-ray. So there's some ratio you expect of how many of these versus the regular sort of millisecond pulsar that we know. And when we look in the center of the galaxy, we actually don't see anywhere near enough of these things to actually explain the signal. So that is also a mystery. Why aren't we seeing these signals in X-ray if it really are pulsar, but it's not actually there? Right. So another thing you might say is, well, if it's just pulsars, why can't we just look in the center of the galaxy, just observe them, measure their spectrum, and then just call it a day? So it would be nice if it were that simple. You could do this if the point sources were something called resolved. So when we say resolved, I mean they're bright enough for you to look at them and know that you've actually detected a point source. So they're bright enough to be individually detected. The thing is, we have looked for these, and so far we've found absolutely nothing that can explain the signal. That's resolved. So the other thing that is a competitor for the dark matter explanation are these unresolved point sources. Now, unresolved point sources are quite faint, so they're too dim to see them individually. But you could imagine if you have a lot of these really faint sources, they could add up to collectively explain this galactic center excess signal. So these are the things that we want to consider as the competitor for the dark matter signal. Okay, so now the question is it dark matter? Is it these unresolved point sources? These really faint millisecond pulsars. So we'd like to be able to tell the difference between the two. So how do we do that? Thankfully, there is a way, we think, to distinguish these two different types of signals. So it comes from the statistics of the gamma rays that we get from dark matter versus those we get from these unresolved point sources. So the counts of gamma rays from point sources exhibit different statistical behavior to that expected from annihilating dark matter. You can see this on the right here. So this is just a simulation taken from this paper. So in the dark matter only case, it's approximately smooth. This is kind of what you expect. You have dark matter in some smooth halo, it just annihilates. And you can have some fluctuations that just follow Poisson statistics because you know exactly where the dark matter is. The question is just how many gamma rays you'll get from the annihilation. When you compare it to point sources, you can see immediately, even by eye, this looks very different. The point source signal, as I was saying earlier, is much clumpier. Just from, you could imagine, if you take all your data, you pixelize your data, in a given pixel, you might have absolutely no pulsars, and you would get no gamma rays from each pixel. But in another pixel, you might say have like 10 of these things, and they could all then give you a lot of other gamma rays, which get out to give you a lot. So pixel by pixel, there are much more fluctuations in this point source scenario. So because they're clumpy, it ends up being that they follow non-Poisson statistics, which is difficult to characterize. The reason you have to have non-Poisson statistics is you first of all have to have a Poisson draw for the probability you even have a point source in your pixel. There might be none, so you can do one draw. Then you need to do an additional draw for how many gamma rays are you getting from your sources. So this becomes complex to characterize, but the main point is you get drastically different predictions. Pixel by pixel, you can get a lot of variation from point sources. Dark matter, nowhere near as much. Okay. So what I want to do now, keep in mind, I want to answer the question, what is explaining this galactic center excess? I'm going to use the fact that these two different dark matter versus point sources, these two different competing answers to what might be giving you the excess. They follow different statistics. So I then want to build up a picture of the gamma ray sky based on some model, ansatz, or a catalogue of things we already know. And I want to put these different statistics on these different templates. So this is what I talk about when I say templates. So these are just things that we expect to be in the galaxy already, or we already know are actually there. And when I go through and put different statistics on these different shapes, add them up, do some statistical fit, I want to see then what is the best fit. Do I want to have clumpiness along different shapes, or do I want to have a smooth fit along different shapes? So just to be a bit more clear, these are the templates I'll be considering. So you have some isotropic signal, which is the one on the left here. You might notice this doesn't look very isotropic. It's not exactly smooth. The reason for this is you have to take into account the instrument response function, being that when Fermi looks for gamma rays in the sky, it doesn't look at all parts of the sky evenly. So if it's looking somewhere a bit longer than it's looking somewhere else, it makes sense, it would see a bit more, and that's corrected for in these templates. You can see where Fermi was looking more than other places. So another template we include is this diffuse background. Now, diffuse gamma rays, this is the largest by far background you have in gamma ray searches. So this makes up, in the region of interest, we're looking at like 80 to 90% of the gamma rays. And the thing is also, we don't know this super well. So this is kind of the most kind of questionable part of what you're doing, how well do we understand these diffuse backgrounds. Where do they actually come from? They come from cosmic rays interacting with the disk of our plane, as well as inverse Compton scattering with the starlight. So we also have the bubbles here. I think this is stopped. If you point to stop, so I'll just not point. So on the right we have the bubbles. So the Fermi bubbles are this giant gamma ray structure that extend well above and below the plane of our galaxy. No one really knows what's going on with the Fermi bubbles, which is a separate question for a separate talk, but we know at least they're there. So we include them as a template. So we know there's some distribution of gamma rays above and below. Have to put them in because we know it's there. And also, most interestingly, I'm going to put in an NFW template. Now this NFW template is effectively, you can think of it as the excess template. So this is roughly the morphology of the galactic center excess. So if I put in the smooth statistics, or Poisson statistics, that is effectively a dark matter signal, but we're putting in a template for something smooth there. I'll also want to put the point source statistics on this template, because the question I want to answer is, what is the better fit? Something smooth, dark matter-like, that has the morphology of the excess, or something more clumpy? What is the best fit? So before I show you the answer, I'm going to give you just a little bit, just a few more details so you can properly understand what the results mean. So when we do Poisson template fitting, so this is just the smooth backgrounds. So when I say smooth, it can be the dark matter signal, but there are other backgrounds as well that have this sort of smooth distribution. So what you do is you take all of your data. So we'll take the Fermi data, going to pixelize it, and then for a given template, so you see I have this mu here. So this is the mean prediction per pixel. So P is the pixel index, and 1 is the template. So I'm looking at the top one, that's the template index. And the only free parameter that I have when I do this fit is the normalization. So that's what the alpha 1, alpha 2, alpha 3, alpha 4 is. So we already have, within some templates on shape, some mean prediction, and I want to float all of those normalizations. So the prediction for each pixel is, I'm just going to sum up this mu of P. So you can see the normalization is this alpha times the mean prediction. The likelihood per pixel is just a Poisson distribution. So this is the standard sort of thing you've seen before. This theta is just all of the model parameters. So the total likelihood that you're going to get is given by the product of Poisson likelihoods for each pixel. So this is just standard Poisson sort of statistics. So we're going to be working in a Bayesian framework. So what we want to do is we want to have some priors for what we expect. So just based on physical motivation, what the normalizations should be. So we have some range for how large they reasonably could be. And then we want to find the posterior distribution. So this is just, I'll put in, I think that the range for these values is in a particular range. At the end, I want it to tell me, okay, this many gamma rays comes from this particular template, which should give me a breakdown in the end.
I have a question for your diffuse galactic model. Is that from Galprop, or is that just something that's matched?
This one is the Fermi P6B11. We do also look at the ones from Galprop as well.
Okay, but for your... Okay.
This one here, that one was P6B11. So everyone else, that's Fermi's. Okay. Right, so the difference with non-Poisson template fitting is you have extra degrees of freedom because for these, if you imagine you have some source populations, so some new population of pulsars that's shaped like the excess. I want to find a way to characterize, first of all, how many of these point sources I have, but how bright they are. So how many I have of different brightness, effectively. So if we want to model this, you just take a broken power law. So that's what this dNPS is. So it's the number of sources you have as a function of their flux. So there's 3 additional degrees of freedom. So what you want to look at, just as an example, take this blue one here. So this is the flux, so the photons we have, and this is effectively the number of sources you have with the given flux. So you think about it as number of sources you have with the given brightness. So if you just have a look at the blue one, so this is an example as, I think this one was one of the best fits for the Galactic Center Excess. So all you need to know is, I have still the normalization, for just how large the overall signal is, but I also have the slope of this, it's a broken power law, so this line here, that's allowed to float, so we can go up and down. This one here also is allowed to float that way. And there's also a break, that's this part here, and that can move around however it likes. And what you could think of is you could imagine, okay, I have this many sources at this brightness, I have this many sources, and you can just see how many there are along the pool. So we want to float all of those parameters together in one fit. I'm going to skip over some more of the technical details. Right, so finally a result. This was the 2015 result that really thoroughly challenged the dark matter interpretation. So what they did was, for the first time, they applied this non-Poisson template fitting method to ask the question, is it smooth, is it cocky? So you can see inlaid here. This is if you don't put any point source templates, so no GC point source, no millisecond pulsars at all for the excess. And the red thing here is a dark matter signal. That's the thing everyone was excited about before. Look, we have a dark matter signal. So you know, in this region of interest, this is the flux. So this is about 7% of the flux. This is the posterior probability. But you see it's peaked at about 7%. That was the size of the excess in that region. So they said, look, it's dark matter. They added this extra template with the clumpiness, and they found this is the bigger plot on the outside. Red was the dark matter. You see this has been pushed to 0. And instead, this orangey sort of thing, instead around 7%, that's the GC point sources. So they found that the best fit, once you allow in your model to have these point sources of the excess, that this was the description of the excess. And they found this with a very large base vector. So it just means with a very large statistical preference. This by far was the benefit compared to not having point sources. And you see the dark matter is pushed to 0. So really this was a massive death blow for the dark matter interpretation of the excess. And at this point I think a lot of people really started thinking, well, okay, probably not dark matter, that was fun. Oh well. One other thing I was explaining to you is source count functions. This is the broken power law that describes the distribution of the point sources of flux. One really interesting thing that they found was looking at this orange curve here. This is the GC of point sources. Fermi sensitivity actually is just here. So that means what they were finding was the excess is best explained by some new population of unresolved point sources, but they're just below what Fermi could see. So we just missed out on signal. Okay. So what did we do? So we asked the question, what's driving this preference? Why do we see a preference of point sources over dark matter? In particular, we wondered that if you weren't actually modeling something correctly, for example, imagine there was an extra source population and you weren't taking into that account with all the different sort of templates I was showing you. Is it possible this could push up the GC point sources flux and push down the dark matter flux? So I wanted to investigate if a bias like this is possible in two different ways. First of all, in a simulated proof of principle example. The reason usually you want to do things in simulated data, at least in the beginning, is when you simulate data, obviously you know what you put in. So if you simulate something and then you analyze it and it doesn't come back the way you expected, something's kind of gone wrong in general. So first,
I'm sorry, on your previous slide, what is the energy range for that flux? Is that like
for which?
100 MeV, 1 GeV? What's the?
Which
That's the integrated flux.
This?
Yeah, that one on the right. So that's the flux. Do you know what energy range that corresponds to?
What energy range the photons are?
Yeah. So.
It's around a few GeV.
So a few GeV and above.
Yeah.
Okay.
For this, at this analysis, I think they did 2. All of the photons, I think, were 2 to 10 GeV. I think. Or we have 2 to 10 and they did 20. Something like that.
Okay, because what I'm trying to get, if it's to the point source, or when you get too low energies, it's substantially degrade.
How could you actually tell if it's dark matter versus point source and they're faint?
Yeah,
you can't tell they're the same. So where that actually happens, so that's where the point sources emit either 0 or 1 photons, the same as dark matter. That's around here. That's the 1 count threshold. So anything below here, you can't tell the difference between that and dark matter.
Okay.
Okay. Right. So I'm going to show you an example with simulated data. And also, we want to know if this is happening in the real data. And of course, the complication with the real data is you don't know exactly for sure what's in there. So you can't say, I've got this combination of templates, they're definitely correct. You just don't know. But it turns out, based on my simulated proof of principle example, I have an idea how to test for this in the real data. I'll show you both of these. So the first test we did using simulated data was putting point source in the Fermi bubbles. So before we did this analysis, no one had tried to put point sources in the Fermi bubbles for this particular type of analysis. And this wasn't, totally crazy. It turned out about a year ago, there was a paper finding that there were potential gas clumps in these Fermi bubbles, the big structure above the galaxy. This one here. So while if there are sort of gas clumps, these could look like point sources in what we're doing. So it made sense. Maybe there are some point sources in the bubbles and they're throwing off a true dark matter signal, for example. Then we simulate everything else. So we simulate the backgrounds, we know that should be there, so there's just point sources along the disk. All the other backgrounds, but importantly, we're also going to simulate a dark matter signal. So I'm going to put point sources in these Fermi bubbles. I'm going to put a dark matter signal as well. I'm not going to simulate any GCE point sources at all. Okay. So first of all, I want to analyze this data with exactly the same templates as what I simulated. So I'm going to give it the bubbles point source template as an option. I'm going to give it a dark matter template as an option. And it finds everything just fine, which is good. So I injected about 2% dark matter flux. You see this TM here, it picked it up fine. This is about how much of the flux I put into bubbles point sources. It got everything back okay. So that's good. That's just a sanity check to make sure everything's going okay. So now this is the exciting part. So what I want to do now is simulate point sources in the bubbles. I'm going to drop that template, and in its place, I'm going to put GCE point sources. Now I didn't simulate any GCE point sources. 1, does it find the dark matter? 2, does it find GCE point sources? GCE point sources were not put into this simulation. Indeed it does. So in this scenario, the dark matter signal is misattributed to a point source signal. So you see dark matter here, peaked at 0, injected dark matter about 2%. It didn't find the dark matter, and instead, it found a new population that doesn't even exist. This was not in my simulation. It's found these NFW, GCE distributed point sources. This is very interesting. We've just found a way that if there was really a dark matter signal there, the fit would think there's no dark matter and that there were GCE point sources. So we kept adding more and more dark matter just to see, is there some threshold where it actually finds it? So added a few percent more. You see these, I think I also forgot to say, these dashed lines, I think are the 1 sigma containment. So in this case, the NFW point sources, GCE point sources just got pushed up more. Still didn't find dark matter, the bands are a little bit wider. And then we can put in a lot, and eventually it actually does find it, but it didn't find all of it. So in this case, I injected about 15%. It picks up maybe like 12 or 13 in this case. So if I put in a lot, it finds it, but GCE size, it didn't. So this is the first evidence of a misattributed dark matter signal using these methods. So we found that crosstalk between templates appears to be possible if you have some unmodeled component in your data. So if there's something else and you're not including the template, you can totally throw off what your conclusion is. And you could be We find this behavior is possible in a masked and unmasked sky. So what I mean by that is, there are the really bright sources we know exist. They're not part of the excess. You can just block them out just to try and get rid of anything you don't need. You still find it. We look at different regions of interest, and we find you can still see this sort of behavior. But really importantly, we find a large base factor in preference for these GCE point sources and for pushing the dark matter down. And this is just like this 2015 paper. But in this case, we know dark matter is there. So when I compare the two fits of when it gets the dark matter back correctly versus thinking dark matter 0 and there's an extra population that doesn't exist, it wants the wrong scenario. So the statistical preference is actually for the wrong thing. This is the same sort of behavior.
I have a question, basic question. So if you're trying to create the templates, basically, I'm questioning the templates. If you're trying to find out if there's a new physics and using the templates created from the distribution you have, that would be biased, right? So did you create your templates from a priori or from different galaxies, dwarf galaxies or something, I don't know. How did you create your templates?
Yeah, so these just come from either like a model ansatz or a catalog of something we already know. So for example, for the GCE, we just put in literally this generalized NFW profile, because that is roughly the case it's found to be the best fit for some diffuse models. For the diffuse models, because we were using a particular type of the Fermi data, we used, so the diffuse model, Fermi has different versions. We used, and that's the one that's the main background, we used one of the older versions of that template because any of the newer versions had other things, for example, the bubbles already built in. And if you're doing template fitting, you don't want other things already built into one. You want to separate them. So that was the last one they had that did that. Anything that makes a big difference to your background, such as this diffuse model, so for what you're saying, then you want to test other ones as well to check that you're seeing a consistent picture when you change this. So we did test using different background models, and we found similar sort of behavior that you wouldn't find the dark matter signal as well. In terms of the other ones, you can vary them, but in the past studies, they weren't found to make a qualitative difference to the statistical preference or the best fits generally. There wasn't anything that was found before that if you changed it, when you already spanned a reasonable sort of set of particular assumptions, that it drastically changed the answer. But definitely, if you had something that's wrong, yeah, that's part of what we're saying. If it's not modeled right, it can change what your answer is.
And the second question is your point sources, like the pulsars, asymptotically, they would approach your dark matter.
That's correct.
Right, so depending on, do we actually know how many point sources should there be?
For the faint end, you can't tell the difference, so that's right. But in the case of, so part of what I was showing you before with this fit, these are really bright. So I think it's pretty difficult to get dark matter to mimic this. And I think these give you the bulk of your flux anyway. So these ones that are really bright, those ones, at least in this scenario here from 2015, they're not degenerate with dark matter, and because they're so bright, you add those up, they're what actually gives you effectively all the excess. So I think even if you chopped the faint in, I think they're not adding up anything much for this case. It depends what this population looks like. If this was different, for example, if it was really steep, then that would be a different case.
Thank you.
So the next question is, so I just showed you could use these Fermi bubbles to throw off a dark matter signal. So the immediate next question is, are there actually point sources in the Fermi bubbles? That'd be super exciting, because if it is, we're like, oh, we got dark matter, and those bubbles were the one that did it. So we're like, okay, we better check, just are there point sources in there? And the way you want to do this using these methods is you just do a fit without the bubbles point sources, because they're all the regular backgrounds you know, and then you add the bubbles point sources and you just see just the statistical preference change. Like, does it prefer to have point sources there versus not there? And if you're worried about the complications from the center of the galaxy, the bubbles actually go up very high in latitude, so you can just mask out, so just block out everything lower and just look at the top and see if they're there. But we check different latitudes. So we're going to look through different regions of the sky, just see if we find any of these point sources or not. So we've got all the backgrounds, so you don't need to know so much. So this is without bubbles point sources. Maybe you can see foreshadowing what the answer is, because this goes down to like tiny, tiny values. This is the isotropic background in point sources that exist, just a background. High latitude is going to add the bubbles so we see them change. The bubbles is this thing here, which is effectively 0. In terms of the flux plot, it's the blue thing heaped at 0. And if you check the base factor, which is statistical preference, when you add these in, nothing changes. So the point of this is, we find no evidence for point sources in the Fermi bubbles. So what did I just push you through? Why did I just tell you this story? The point of these bubbles in the simulated data really is just a proof of principle case, that if you have some combination of templates and it doesn't really, when you're analyzing it's not actually what the real data is, it can just change what your answer is. So if you're not modeling things correctly, you can hide a dark matter signal. That is the only point of that story. But we would like something more substantial than just a proof of principle case of how this can kind of go wrong. We want to know if this is happening in the real data or not. And as I said earlier, a complication is in the real data, you don't know what's there. But one thing that we saw in this simulated proof of principle case, remember I kept putting in more dark matter? And when I kept putting in more dark matter, the GC point sources flux kept increasing. So when I put in, say, 2% dark matter, GC point sources went up by 2%. So if this is happening, or something like it is happening in the real data, we can inject an artificial dark matter signal into the real data and just see, does it pick it up? Or does it also, similarly to our proof of principle case, just misattribute it to these GC point sources? So that's what we're going to do. We're going to try this now in the real data. So on the left is the Fermi data with no dark matter injection. This is the 2015 results. So this is the GC point sources, and then some other backgrounds. There's no dark matter. You might remember earlier I told you it was about 7% of the flux. We're just looking in a different region of the sky. So we've zoomed out a little bit more, but we find the same behavior. So these plots I'm showing you, GC point sources, all the signal, dark matter, 0. Okay, so now first of all, I'm going to inject dark matter signal about 2% of the flux. So you want to watch what happens to the red line, that's the line on the left, and the NFW point sources. 2% flux. In the real data, if I put 2% flux in, what happens? It doesn't know it's there in the real data. So I put a 2% dark matter signal in, dark matter still is peaked at 0, and GC point sources has gone up. This is the same qualitative behavior we saw in the proof of principle example, and it's the real data. So something's going on. So we could try then just adding in more dark matter, similar to the proof of principle example. So in this case, I'm going to add maybe about 6% of the flux. So you want to watch what happens. If it picks up dark matter, you should see dark matter peaked at 6%. If it misattributes it to a point source signal, this should go up to around, the purple NFW point sources should go up to around 8%-ish. What happens? Still doesn't know it's there with this. So I've injected almost 7%, injected dark matter. NFW point sources has absorbed almost all of this. The dark matter is still peaked at 0. Still not finding the dark matter signal. This is a signal that's like 3 or 4 times larger than the actual excess. And it's putting it all into this template instead. So we can then just get sick of this and be like, okay, at what point is it actually going to find the dark matter? So we can bombard the galaxy. So this is the real Fermi data. I'm going to put a dark matter signal that looks like that. So the center just blew up. That's a massive, massive signal. So like an order of magnitude larger in its normalization in the Galactic Center Excess. Does it find it then? Finally, it does. And so if we see here, there is some dark matter signal that is found, but it clearly hasn't found all of it. But you need to put in about this much of the dark matter signal before it actually finds anything, and it still won't find most of it. An alternative way to understand what's happening is, at one point, we started thinking about this degeneracy between dark matter and the really faint point sources, and maybe you think maybe it's just being absorbed in the faint end, and maybe that's why it's happening. But the thing is, the source count function really didn't want anything at the faint end. The sort of shape that we were picking up wanted nothing there, and it wasn't finding dark matter. So out of interest, we're like, okay, physically this makes no sense, but what happens if we let dark matter's normalization just go negative and just see what happens? And what actually happens is it goes really, really negative. So this is when we let it do that, and we apply a range to like dictate what it's allowed to do. Before it was heaped at 0, if you let it go negative, it's not actually properly, it's not physical. If you had a physical sort of well-defined scenario, it should be pretty close to 0. Instead, it goes really negative, and you can actually roughly think of this is why the injection test is failing. So remember I showed you examples I put in, say, 2%, 7%, something like that. It never found it. So we actually tested like letting this keep going negative at say 2%. You see this just moves up like 2%. And until I put in like 15%, remember it didn't find all of it, but it found some. Because 15% is enough to overcome this -8, just where it's centered, to appear roughly over here. So it's not until you put in like this much percent that you actually find it. Right. So I've shown you a simulated example and a real data example with similar sort of behavior. So just also for reference, the simulated data case also went negative. Not as badly as the real data, but it went negative, which explains part of why it's happening. And in all cases, we found very significant statistical preference for the wrong case, being it kept finding, in the simulated data, it kept finding something that didn't exist and no dark matter. In the real data, we injected a dark matter signal and it kept not finding it, and then wanting the scenario where you didn't find the dark matter. So we saw that a potential dark matter signal very clearly could be incorrectly discarded, and this could be due to some other unresolved point source population that we're not modeling, which is any other point source population that we're not modeling, or some mismodeling in general. If one of our templates is not modeled correctly, that could also be something that's doing this. So what this means for dark matter is really that the upper bounds on dark matter annihilation can be really badly misestimated. So you shouldn't think of this as like a bound on the cross-section, but you can see clearly that if it doesn't find the dark matter flux and you think, okay, it should be 0, I mean those bounds in the first case showed it was just heaped at 0. The fact it didn't find something that was like several times B in the excess shows you that if you find 0 doesn't mean there actually is no dark matter there. And indeed then dark matter could substantially contribute to the excess after all. It could actually be the thing that's behind it.
I have a question. Isn't that more like a fitting issue than physics? I mean, there's nothing profound in what you just said. It goes to 0. It's more like a fitting. Like I could take it in priority that dark matter cannot be more than 5 times less than a point source. And I could actually recreate proper, because you let it float, that's where it was going to be. I mean, am I seeing something more profound, like physics-wise, or just it's a fitting issue?
So I'll tell you a physics reason in the next few slides, which is I'm about to tell you about some of the things that we're doing since to understand this, which I should be doing quickly. In this case, it's just that it wasn't finding the dark matter, and I think what that means is really that our understanding of the best way to model the gamma ray sky was not correct, I think is what that means. So whenever we model something in simulated data, if we ever analyze it with the same templates, we always roughly got the right thing back, which meant that, okay, the method's fine, the method works just fine, but if you don't model things correctly, you'll get the wrong answer. And I think that's a very important statement, because particularly like what's at stake in terms of understanding the signal, and I think particularly around 2015 we were thinking it's not dark matter because look, we see dark matter peaked at 0 and we find evidence for point sources. But if you're not modeling things correctly, that doesn't mean that's the right answer.
There's a reason why in dark matter direct detection analysis we don't use a Bayesian approach, we use a Fermi cousins, right? There's a reason for that, and I'm starting to see it, but I have to give it 5 minutes.
To show you this. I think this died, so I'm going to have to overtake. Okay, so just quickly some further investigation. So we tried other combinations of different point source populations. We didn't find this effect with anything other than the bubbles. But one thing we want to do is then just break the sky into different regions of interest and see if it's just a particular region of the sky causing this problem. So this is the preliminary work that I'll show you very, very quickly. So this is the center of the galaxy. We've masked out +2 - degrees of latitude. So we're going to look just in these individual regions here. So recently, actually, also very interestingly, a preference for smooth emission was found outside 5 degrees, which is this region up here, by a few authors last year. So we want to see, do we see a similar thing or do we see something else? Can we do some tests where we break the sky up into different regions instead of just having one template for dark matter or point sources within the whole region? So this is kind of more of a model-independent approach to try to see what's happening as opposed to just changing a lot of different templates. So first of all, if I take just this region, so the sum of all these regions, one dark matter template, one point source template in this particular shape. You see again, dark matter is still negative. If we let it go negative, we find some NFW point sources. Now what we want to do is, we want to see what happens if we allow instead an asymmetry. So the first thing I'm going to show you is, I put one GCE template across these two in the south, and one GCE template across those two. So I've split it into two. North-south can do their own sort of thing. What happens if we allow the excess to do this? Actually, then it's well behaved. We find this negativity goes away. We find some smooth dark matter-like components in both of the regions, and we find some point sources. Interestingly, this is actually preferred significantly. So we find really, really large base factors for splitting this template into the two different regions. The north appears to be the north appears to be brighter. You notice also, I should probably clarify at this stage, pick up these dark matter components, this is preferred, and it's preferred over this case, and it's physically well behaved. At this stage, a very important point is, as a few people have mentioned already, dark matter-like, one, you actually can't tell the difference between dark matter and really fake point sources in this method. So it could be these are just literally the really fake point sources, but this is as far as the method will take you. It's just something smooth along this template picks up. And now for the juicy part, unless you think that was juicy enough. Best fit behavior in simulations. We want to see, can we reproduce this behavior in simulations? We've never been able to do this before. So first of all, I'm going to make some simulated data based on the best fit to the real data. So the best fit we find to the real data now is a GC that's brighter in the north and a bit fainter in the south. And we want to check if we recover all the components. And we find we generally do. We get up exactly what we simulated. But now what I want to connect this to what we've been doing earlier, what everyone has been doing in the past for these sort of settings. So I'm going to use the same simulated data from the best fit, which is asymmetric GC, brighter in the south, in the north, fainter in the south. And I want to analyze it only with one symmetric template. So one GC template over the whole region. What happens? It's negative. This is the first time we actually found something like this that actually happened. This is just as negative as we were seeing in the real data. So you can compare the two cases. This is simulation, this is real data. We find the same base factors, the same statistical evidence that is actually happening. And we already found that actually the data was better described by an asymmetric galactic center excess. So maybe this is what's happening. We find evidence for asymmetry in the excess, preferred significantly. So the failed injection test for the negative dark matter is alleviated by allowing just the GC template to have more freedom. So if you just let it move around a bit more, it actually seems to behave better, and simulations and real data seem to be behaving actually exactly the same. I should also highlight at this point I've got preliminary, but everyone else can't see it, so this is still not released yet, so we still might have some things to change a little bit. Also, very interestingly, we find strong evidence for point sources when you analyze with one template over the whole region. But when you break it into this north-south floating separately, you actually almost lose your preference of point sources. Like, it's not statistically significant anymore to even have that. So this is really interesting. So just when you think you find evidence for point sources, doesn't actually mean point sources are there. This is the first time we've seen something like this as well happen. It also picks up a dark matter-like component. Important to note, you actually can't tell the difference between this and just really faint point sources, or anything else that's just NFW shaped and is smooth. Could be any of these things. And we find a truly positive dark matter component can appear negative, just if you don't give your GC template enough freedom. Okay, 1 minute. Moving forward, how can we tell the difference between pulsars and dark matter? If it actually is pulsars, it turns out in the end, thankfully, we will maybe know in the next few years, maybe. So there are a few experiments that could look at these pulsars directly. So potentially these millisecond pulsars can pulse in the radio, and then you could use radio telescopes to detect them. So specifically, you could use MeerKAT, the square kilometer array, SKA. So this is just the bulge population of point sources. They claim to have some sensitivity to some of these. So maybe we'll just see them directly. If we start seeing some of them, you'll be like, well, okay, maybe that's actually what it is after all. If it's dark matter, we really want to see it somewhere else. I think no one's ever going to believe a dark matter signal from the center of the galaxy just because there's so much that's going on. So you just want to build up a consistent picture. So for example, with these dwarf toroidal observations, so these are really dark matter dense galaxies, very low background. If we start seeing something consistent there, that will be exciting. Also, there's this tantalizing overlap with the antiproton excess. So there's an excess detected at the moment, antiprotons. Of course, you might say something like, how well do you understand your cosmic ray propagation, or those sort of uncertainties. But that's a separate question. But in any case, they do overlap on the dark matter parameter space, so maybe we're actually starting to see the first signal in dark matter. Okay, so in summary, the GCE is very firmly detected. We know it's there, we just don't know what it is. So what I showed you in this talk was some studies we've been doing to, first of all, we tested if you had some unaccounted for point source populations, could they just bias your result? And we found they could. We found in simulated data and in real data, you could hide a dark matter signal. Even if it was really there, then you wouldn't find it. Yes, good. I also showed you some preliminary work at the end. So we find there's some asymmetry in the GC itself, and this had pretty solid boost factor. And if you don't actually allow the asymmetry, which is what no one had been doing before, you can push the dark matter template negative. And when you update with this asymmetry, you can lose your evidence for point sources altogether, and you get some smooth signal instead as the excess, which is not point sources, but again, they emphasize it. And moving forward, if we want to find dark matter, we need to see this in other places. And there is a tantalizing overlap with another signal, but it still remains to be seen if it's actually dark matter or pulsar signal. Thanks.
Thank you, Rebecca. Any questions?
Else, like something else is dark matter, like boosted dark matter, with a little bit different distribution. Would you be able to see the difference between the pulsar distribution and dark matter in that?
So how would your distribution look if you had your
No,
boosted?
so boosted means say some dark matter produce annihilation of two dark matter produce a high energy dark matter, and so that means it has a larger
It's more
velocity.
like yeah.
Right. So
Um,
wouldn't it kind of look different from your like point source?
Right.
If
So
you have a halo of
yeah.
distribution.
Right, so then you could do a fit, for example, with one other shape that it had, and then keep, I mean, the excess has a particular morphology. So the way that was found originally was just pitting all the backgrounds and then effectively removing them and just seeing what's left. And you see that kind of roughly spherically symmetric. So if your boosted dark matter didn't predict something that looked kind of like that, then you'd have to answer, if you wanted to claim that was explaining the excess, then I think it'd be more difficult. If the distribution is wildly different, I don't know how different you
So
expect
it
it to
would
be.
be still spherically symmetric because
Right.
it can go in any
Yep.
direction, but it may be different from the pulsar.
I'm not sure that if using this method, if the photon you were getting from it were the same, if you would be able to tell the difference. Because all this method is doing, also like we're not actually extracting with this non-Poisson template fitting anything about the energy spectrum. It's just one energy bin. So if you had the net same amount of photons coming from this and the same shape, you can't tell the difference. But maybe there's some other smart way, something else you could do.
I have a crazy question. So if you have a dark matter substructure,
Yep.
say, which is no star associated with it, that's a non-Poissonian signal too, right?
Yep.
Because there's a point source which you detect as
Yep.
a diffuse signal.
Yep.
At what point do you start thinking about those?
Yeah, it's a great question. So the thing with that is if you have more of this substructure, why you expect the distribution to look this way. So I think then that's an extra step in tying it into having this NNW-like, because it's not just the standard annihilating, so it's not the same template that you would have anymore.
So you have like a non-Poissonian
Yeah, so if you had that, then effectively, I guess, then I guess in that case you couldn't tell the difference either. But I think the problem is usually just for this standard dark matter and the standard halo, it very nicely pulls out why you have that distribution. And I think when you have more of this clumpy sort of dark matter, it's like, why would you expect it to be distributed using that W profile?
Yeah, I mean,
simulation,
that's-
for example.
Yeah, so the problem with what I just said, of course, is like the galactic center is probably not the place to find these objects. But, okay.
Any other questions? Right, let's thank Rebecca one more time.